And so to covalent bonds. So we looked at the idea of a metal ion having very few outer electrons given by this number on the groups, and it would tend to lose those electrons in a reaction and become a positive ion. And the non-metals would do the opposite because they have a high number of electrons in their outer energy levels and don't need to gain many electrons in order to become stable. So they gain some electrons, which they get from the positive ions, and the negative attracts the positive by electrostatic attraction. And you'll remember that they don't form molecules, but ionic compounds are crystals with maybe a 1-to-1 ratio of sodium to chloride ions, but many, many thousands or millions of each type. And the formula NaCl, being Na1 to Cl1, is simply a ratio rather than the number of atoms in a molecule. And so now we're going to make molecules. And we're going to make molecules by the process not of ionic bonding, but by covalent bonding. And before I go further, you'll notice I've simplified the information in my periodic table, because it was too difficult to use with all those like 3 or 4 circles when I got down to group 4. All I'm interested in is the valence electrons, the outer electrons, the electrons in the outer energy level. And so that's all that I've put down here. So now we're going to look at covalent bonding, and co has indications of doing things together, cooperating, and it's about sharing. And valent is about valence, electrons. So these bonds are where 2 non-metals share valence electrons. And here's why. If there's a bunch of non-metals, like, let's say oxygen and fluorine together, they're not going to be able to get electrons from a metal because there's no metals around. They have to react with each other. And so what they have to do is something that involves sharing their electrons, because their aim is to become like this. It's to have their outer energy level full, to have the number of electrons in their outer energy levels that helium, neon, or argon have. So let's have a look at how they do that. And the one I choose for this first might be quite a surprising one. It's hydrogen. Because hydrogen, yeah, I know, it can lose an electron and become a positive ion. But when it's reacting with non-metals, it forms a covalent bond. And this is how it does it. Let's say we've got hydrogen, and it's got 1 outer electron, 1 valence electron. And let's say the only other thing around is hydrogen. So what it can do is share those electrons. It can form a covalent bond. And what it does is simply bring its outer energy levels close, so they intersect like a sort of 3-dimensional Venn diagram made out of 2 spheres. And when we draw a covalent bond produced by 2 hydrogen atoms, we place them there. And now this satisfies the criteria of hydrogen to achieve stability. It's got 2 electrons in its outer energy level. Only just, but there they are. And so has the other one. Now it's like this tenuous Venn diagram, where by sharing electrons, they manage to satisfy the need for both atoms to get 1 extra valence electron. So let's have a look now at the most common molecule that we look at. This is, of course, an H2 molecule, hydrogen gas, a very, very rarefied gas, which is not very dense at all. But let's have a look at water. Water is, of course, H2O. So here we've got oxygen. It's in group 6. it's got 6 outer electrons. Good. And what it might do is form a bond with a hydrogen. So I'll put that here. So here's your hydrogen. And what the hydrogen does is bring its electron to the party, and then it needs another one. So here's your oxygen. Gives it one of its electrons. But it doesn't give it, it keeps it. Because hydrogen needs one more electron to become stable like helium. Oxygen needs 2 more electrons to become stable like neon. So right now, the hydrogen is satisfied. It's got 2 electrons, just like helium. But oxygen has now 7. And of course, what happens, because it's H2O, is that hydrogen comes along, shares its electron. One of oxygen's electrons also is shared. And then, because electrons will repel each other and they're in pairs, for a reason we'll talk about later, then these electrons are repelled by the others and they go here into the furthest parts of the outer energy level of the oxygen. And so you get this distinctive V shape of the oxygen, of the water molecule, with a certain specific bond angle. I'm not interested in that at the moment, but what I am interested in is that oxygen now has 8. In terms of electrons, it's stable. And hydrogen now has 2. It's stable, like helium. Just one more before I finish this video. O2 is oxygen. We're aware of that. It's a diatomic gas. And so let's see what happens if I put oxygen together with an oxygen. Whoops, I need to move that. And we'll intersect their outer energy levels, their valence shells, because that's what they do in a covalent bond. So oxygen, it needs to gain 2 electrons. So this oxygen needs to share 2 electrons with that oxygen. This oxygen needs to share 2 electrons with this one. So each one has shared 2, and there's 4 more that they normally have. This one also has 4 more. So each oxygen now has 8 electrons in its outer energy level. Stable. Sometimes this can become confusing. So in diagrams, what's often done is, like for one atom, we show its electrons in a slightly different way. So I've shown them as crosses from this one. And so you can see that the covalent bond consists of 1 electron from this and 1 electron from that. But of course, oxygen, O2, has 2 covalent bonds. And that can happen if it's going to make both atoms more stable.